Hey, you guys, here's your video for our PowerPoint slides for Chapter 9, which is called Chemical Bonding 1 Basic Concepts. This PowerPoint lecture will be through sections 9.1 through 9.5. But anyway, let's talk about chemical bonding. Now, chemical bonding, when you think, oh, I know what a bond is, what is a bond, right? Bond has to do with electrons overlapping. You've probably seen water being drawn your whole life since you were in primary school or elementary school. And you might have even seen these little dots here, which mean lone electron pairs that are not involved in bonding. This is a bond. Now, water has covalent bonds. Then, of course, there's ionic bonds. Now, these pictures here were an idea from Mr. Lewis, who invented Lewis dot structures that helped to visualize where the valence electrons were in an atom. And he looked at them as kind of like little cubes and stuff. And there's nothing wrong with that. I mean, crystal structures actually grow with these, atoms at the corners of cubes. So he was kind of ahead of his time in that area. But let's start right in to chemical bonding and the basic concepts that build on that. So let's talk about Lewis dot symbols. Again, we're talking about Mr. Lewis inventing these Lewis symbols to illustrate the valence electrons in an atom. If you look at this picture, you'll see dots on each elemental symbol, and for each dot, that is a valence electron. Valence electrons are the outermost shell electrons of an atom, and the valence electrons are the electrons that participate in chemical bonding. So when we draw something like H, I just drew a chemical bond, a covalent bond between two hydrogen atoms, and that bond consists of two electrons. Now, if you recall, the outermost electron configuration, this is the general outermost electron configuration that shows the number of valence electrons in those elements of that group. And here they are over for group 3 and 4 and group 5, 6, and 7. Remember that noble gases don't necessarily have, quote, valence electrons because they're all paired up. Now for fun sheet question number 1, you're asked to draw the Lewis dot symbols for the elements or ions. Well, if it's an element, then it has the number of valence electrons in that neutral atom. You'll also notice that the electrons are together. For example, look at calcium up here. Calcium, Lewis dot symbol has a dot and a dot. Now you might think that they would be paired, but I think the reason that they are separated is to show that calcium, if he does form covalent bonds, would form two bonds. There are some alkaline earth metals that form covalent compounds like beryllium. You'll see beryllium in a compound like something like, sorry about my drawing here, beryllium hydride. And those are actually covalent bonds, and he forms two bonds. Magnesium, very similar. We're going to talk about in this chapter the difference between an ionic bond, a partially ionic bond, and a covalent bond. And there's a lot of gray area, so don't worry. So as far as drawing Lewis dot symbols for elements, you would go find the number of valence electrons. Now, if it's an ion, those valence electrons have altered. And remember in cations, those electrons are lost. In anions, electrons are gained. So for example, nitrogen likes to form nitride. And when he forms a nitride anion, he gains 3 electrons. So when he came in with 5 electrons by himself, but say he forms a compound with somebody else, he is now going to gain electrons from that somebody else. And since he gains 3 electrons, he becomes nitride N3-. This would be your Lewis dot symbol for nitride. So go try those and then post them to the discussion board so we can check on each other's work and make sure our understanding is strong. Now let's talk about the ionic bond. The ionic bond consists of an electrostatic force that holds ions together once electron transfer has occurred. So for example, lithium and fluorine like to react because lithium has 1 valence electron and fluorine has an empty space. This might look a little weird because I know that fluorine, and I know you guys know, travels as a diatomic element or molecule. This is showing after that bond has been broken because fluorine will not make a bond unless it breaks that single bond and enables it to bond with something else. So this is after that bond breakage, makes lithium fluoride. This is the electrostatic force of a positive and a negative attracting each other. That's the ionic bond. Notice there is no line. A line between two elements like this means covalent, and it means sharing of electrons. So originally lithium came in with a electron configuration of 1s2, 2s1. Fluorine was 1s2, 2s2, 2p5. Notice the empty space. Now, once they form the compound, lithium has a noble gas structure, and so does of helium, and so does fluorine. Fluorine has now become fluoride and has a noble gas structure of neon. These half reactions, if you remember from chapter 4 in oxidation and reduction, this is oxidation and this is reduction. So you see, you kind of never get away from those. It was a representation of the electron exchange, and if you add these two half reactions together, the electrons cancel out, and you make the whole reaction. Now try fun sheet question number 2, which is asking you to describe the formation of an ionic bond, like in words. How would you narratively tell someone about that? So in your discussion post, type in your own words what the formation of an ionic bond means to you. Then for part B, use Lewis symbols to show the transfer of electrons, kind of like we did up here. And you can even use arrows, like if I want to point it, that's going to come to this spot, to show the transfer of electrons between barium and hydrogen to form barium hydride, like an equation, just like you saw in this slide. Now let's get into a little bit more of an analysis of ionic compounds, and that involves lattice energy. Lattice energy is kind of a weird concept because the only reason for it is to explain the enthalpy of formation of an ionic compound. Recall, enthalpies of formation are given in the appendix 2 in your textbook. So those numbers came from somewhere. They came from experimental as well as theoretical concepts. Lattice energy is the energy required to completely separate 1 mole of a solid ionic compound into its gaseous ions. Now, this doesn't really happen. I guess it does happen if you just heat it up. And if you heat up an ionic compound, it will melt. And once it melts, like say, for example, I take lithium chloride solid and I melt it, it is now lithium chloride liquid. And those things are now separate from each other. It's molten. But then if I keep on heating it, I can actually vaporize it. And all the energy that I put into that is called the lattice energy. Now, I was afraid that was going to happen, but the way we explain lattice energy and the magnitude of the number associated with a compound is how close substances are to each other, the ions are to each other in the ionic compound, and the charge on the cation and the charge on the anion. These are defined here. E is that potential energy, which is the energy given off when an ionic compound forms, potentially. Q positive is the charge on the cation. Q negative is the charge on the anion. R is how close they are to each other. So let's look at some examples. We have a contrasting here of magnesium fluoride versus magnesium oxide. The lattice energy for these is indicated. Now you can see that magnesium's oxide lattice energy is much larger, and that kind of makes sense because the charges on the cation and anion are larger, therefore their energy is larger. If you look at this formula right over here in the numerator, you will get the numerator is the product of the charge on the cation and anion. So that's directly proportional to this energy. Let's look at another example. Lithium fluoride versus lithium chloride. Lithium fluoride lattice energy is 1036. Lithium chloride is 853. Now you'll notice the Q's on these are +1 and -1 for both. So that is not the factor that can explain the differences in these lattice energies. It must be how close they are to each other. Lithium and fluorine can snuggle up much closer because their sizes are more comparable than lithium and chlorine. These are too far apart, so it's easier to break their electrostatic attraction, hence the lower lattice energy. So lattice energy, remember, increases as this charge increases and as R decreases. snuggling here. If they are snuggled together, their energy is higher. So go look at fun sheet question number 3. You're asked to specify which compound in a pair of ionic compounds, kind of like we did just here, has a higher lattice energy, and explain the reasoning for that based upon the charge or the radius. Now let's talk about some fun stuff with this Born-Haber cycle. Now you thought you were finished with thermochemistry and Hess's law? Not yet. Lattice energy, again, is the energy required to completely separate 1 mole of a solid into gaseous ions. The reason for this is it explains the enthalpy of formation of an ionic compound. So we are going to use the Born-Haber cycle or Hess's law, it's the same thing, to determine lattice energy and to look at the enthalpy of formation of an ionic compound. I know this is a little small, hopefully you can see it on your screen, but this little cycle here, this figure, is showing the steps that a compound undergoes in order to create, or elements undergo to create an ionic compound. So first, lithium solid has to somehow be converted to a gas, otherwise it could never react with fluorine. So this reaction is lithium fluoride, is lithium solid reacting with 1/2 of a mole of fluorine. Now that makes our calculations easier, and that's why we use a half there, to make lithium fluoride solid. Now if we run this reaction, it's a highly exothermic reaction, but the steps that go into it must be somehow lithium solid is separated from its buddies in the solid, fluorine bond is broken, and those then now rearrange themselves to make lithium fluoride, and a solid appears. So the steps for this are lithium. Let's look at the Hess's law. This Born-Haber cycle or Hess's law. The steps are lithium solid being converted to lithium gas. Now, if you recall, that requires energy, and that energy is called the enthalpy of sublimation. The next one is fluorine bonds being broken. That is called the enthalpy of dissociation. The next step is, and these steps can be in any order, lithium gas being ionized to lithium ion. If you recall, this is an ionization energy, and you can get this number, 520, from the table out of chapter 8 of your textbook. The next step is fluorine gas becoming fluoride gas. This fluoride is, if you recall, is called an electron affinity. That's the energy that was given off, and it's exothermic when fluorine gains an electron. The next step is the combination of these ions to form the solid. This is your lattice energy, and if you take a peek right up here at this figure, that's this little step here. Now this is very exothermic. So this is technically not the lattice energy. This is the reverse of the lattice energy. Lattice energy is going this way. If you look at the definition up here on this slide, lattice energy is the energy required to completely separate 1 mole into gaseous ions. Now, if we add all these things up, we should end up with the overall reaction. And recall Hess's law. We can go through and cancel out the individuals that are on either side of the equation, and you will end up with the overall equation. If you add these numbers together, all these enthalpies, you end up with this enthalpy, which is Hess's law. So the appendix 2 that you guys use, remember appendix 2 that you guys use for Hess's law, all of these numbers were determined in this fashion. If you know one, you can get another. The more you know, the more you can calculate. And because some reactions are difficult to measure their enthalpies, like these, there's really no way to measure this enthalpy, but indirectly, as we're doing here. So in your book, you have a table here, table 9.1, that shows the lattice energies of all the different compounds. And you'll notice that melting points kind of have a correlation. A high lattice energy means a high melting point. Sometimes you get sublimation of compounds. They don't even want to melt. They just sublime. So these lattice energies have a correlation to melting point, and they also have a correlation to size of ions involved. you'll notice lattice energy increases from lithium iodide to lithium fluoride. Remember, because lithium fluoride can snuggle. Lithium and iodine cannot. Down here, you'll notice these have +2 and -2 charges, and that directly correlates to a high lattice energy. So let's look at fun sheet question number 4. For fun sheet question number 4, you've been tasked with drawing a figure just like we saw in the previous slides that showed how a compound is broken up, or how bonds are broken and electrons are added or electrons are removed. Then I ask you to line up all the reactions showing the determination of the lattice energy, just like Hess's law. But you're asked for calcium chloride. Now, calcium chloride, be careful, because calcium chloride is slightly different in the fact that you'll have a calcium solid plus chlorine. Now, chlorine is a 2 here, but there's no reason for us to put a half in front because it makes calcium chloride. There is your enthalpy of formation. So this delta H that you would get for this reaction should be the sum of all of these individual ones that you find. Now, your goal is to find what those individual ones are, whether or not they're an ionization energy, an electron affinity, a sublimation, or a dissociation. Now, also recall that calcium metal likes to be oxidized to calcium 2+, losing 2 electrons. So in this case, you should be using the first and the second ionization energy, adding them up to get the energy that's associated with losing 2 electrons. So again, I just wanted to go over this slide again because you're going to apply it to fun sheet question number 4. Here's the lithium fluoride example. All this overall is this one. And all of this 1, 2, 3, 4, and 5, you'll see them listed in your figure. And we also used the lining up of the chemical reactions to illustrate exactly the same thing. So it looks like I've made a mistake here. This one should be overall, not number 5. I had already used number 5. So add these numbers up, check it for yourself. If you add those up, they do indeed equal -594.1. So try fun sheet number 4 and post what your answer on the discussion board. Now let's go into covalent bonds. A covalent bond is a chemical bond which 2 or more electrons are shared. That's the key word, shared by 2 atoms. Why should 2 atoms share, do you think? For example, if these 2 fluorine atoms share, they become that diatomic fluorine molecule. Now recall that overlapping to make a noble gas core is what drives bonding. So we have electrons. Each one now feels as though they have 8 electrons. And I guess they do, if you look at it that way. If we put them together and draw the Lewis dot structure for fluorine molecule, you'll see, and then we count, my dots are not very good. If we count, we have 2, 4, 6, 8. Even though he's really only has half of those, he thinks by sharing that he has both of them. So that makes it a stable molecule. And there's the Lewis structure like I was just trying to draw and showing the lone pairs. So that's a single covalent bond as indicated by that one. So for the Lewis structure of water, let's just see how that might work. Hydrogen and oxygen come together in a fashion such that they have 8 electrons. Not hydrogen, just oxygen. Hydrogen only ever can have 2, remember, because he is 1s1, and if he overlaps, then he can have 2 and think he's helium. A double bond is where something is sharing 2 pairs of electrons, such as carbon dioxide. And now you notice, if you go ahead and count, you have 2, 4, 6, 8. That's what the oxygen thinks it has, and so does this oxygen on this side. This carbon, if you count, 2, 4, 6, 8. It also feels as though it has 8 by sharing, so it is stable. And you see that happening right here. A triple bond, by extension, 2 atoms share 3 pairs of electrons. And again, 8 and 8. That's a triple bond. There's a triple bond. So N2, if you look at him as a molecule, each nitrogen has 5 valence electrons, and 5 plus 5 is 10. And if you count the number of electrons in the structure, you have 2, 4, 6, 8, 10. So you don't go over the 10 by sharing with a triple bond. Now, covalent bonds can be described, they have lengths, just like ionic bonds have distances between them. So covalent bonds, in this example, you'll see a covalent bond between 2 hydrogens is 74 picometers long. That's the addition of this plus this radii. That's how radii of atoms have been determined. You might think, did we take a picture of an atom? No. We looked at all the different compounds that these atoms formed, and then by measuring the distance between the atoms, we found out the radius of a hydrogen, or the radius of an iodine. So this 161 picometers, I guess, if you looked at 161 minus what's 74 divided by 2, you could figure out what and that would be just for the hydrogen, and then you could figure out what the radius of an iodine atom is. So these bond lengths here are bond lengths that have been determined by looking at compounds of all of these elements with all different other elements. This bond length is an average bond length for all those compounds that were studied. So the bond lengths, triple bonds, are shorter than double, which are shorter than single, which makes sense because there's more overlap in a triple bond between the 2 elements than there is in a double bond, and then there's more overlap in a double bond than there is in a single bond. So there was an overlap here. We're going to get to this in chapter 10, but this is called a sigma bond. And then you have more bonds, and these are called pi bonds, and their overlap is not as strong, and it makes them, but it does pull them closer together, which makes them shorter. To compare ionic bonds and covalent bonds, this is a table out of your textbook, table 9.3, and just based upon the fact that ionic compounds are transfer of electrons and an electrostatic attraction, whereas covalent bonds are sharing of electrons, they don't have as strong, so the melting point will reflect that. The melting point of sodium chloride is 800 degrees Celsius, but of a covalent compound called carbon tetrachloride, it's negative 23, so it's a liquid at room temperature. These are reflected in these other energetic properties, like heat of fusion. Remember, that's how much energy it takes to melt something. So it takes a lot more energy to melt an ionic compound than it does a covalent compound. Boiling point, same idea. The boiling point of sodium chloride is much higher than this one because of the electrostatic attraction. Molar heat of vaporization, much higher. Density, on the other hand, I don't know about as far as a pattern. It's not as obvious between ionic and covalent compounds, but generally I think ionic compounds have higher densities. Solubilities in water, high for covalent, low for ionic. And that's because water has some polarity to it, so it can attach to the ions in the covalent and the ionic compound, and kind of water can talk to this guy and dissolve him, and water can dissolve chloride also. Not as much for the covalent compounds. So as far as covalent compounds, let's continue to talk about some characteristics of them. A covalent bond can either be called what's polar or nonpolar. A polar covalent bond polar bond is a covalent bond with greater something density. Let's see if this pops up. I'm thinking electron density around one of the 2 atoms. So this is hydrogen fluoride, HF, and you'll see what this is trying to show by this kind of reddish area is the electrons are being pulled towards the fluorine atom more so than the hydrogen. Now, what I just drew here for you is a bond moment, and a bond moment is an illustration of where the negative, here's a partial negative on this end, and where the positive end is. So this is the electron-rich region in the fluorine area and the electron-poor region. So electron-poor means positive. Electron-rich means negative. And you'll see that on the Lewis dot structure on your right. Partial negative, partial positive. There's our electron density. So for bond moments, I ask you in the fun sheet later on to draw bond moments. I just drew a bond moment for you on this molecule up here. So bond moments are dictated by which atom is more electronegative. So what is electronegativity? It's the ability of an atom to attract toward itself the electrons in a chemical bond. This occurs in covalent bonds. Now, if there's a great or very large difference in electronegativity, ionic bonds now are formed. And that's the reason for it. Before those ionic bonds is because of the great difference in electronegativity. Now, electron affinity is measurable, and chlorine has the highest electron affinity, whereas electronegativity is relative. So we compare bond moments. Bond moments have been determined by these measurements, and it was determined that fluorine has the highest electronegativity by creating bond moments, larger bond moments than chlorine does. So there's a little bit of confusion between that, but it kind of makes sense that electronegativity was determined relative to other elements, whereas electron affinity was determined by electron transfer in ionic bonds. So again, you'll get a partial negative positive area and a partial negative area in a covalent bond, which is what this line means when you have a difference in electronegativity. Some electronegativities of common elements here. There's fluorine. Remember on the previous slide, we just said fluorine has the highest electronegativity. So the electronegativity trend is increasing towards fluorine, no matter if you're going from left to right across the periodic table or from bottom to top. Now your book makes mention of electronegativity and oxidation number. If you remember this from chapter 4, now maybe you can understand why these oxidation numbers are what they are. Oxidation numbers are determined in a compound when a compound is formed. So let's take nitrogen, for example. If nitrogen forms a compound with chlorine, for example, we can make something like NCl3. But let's say I want to make a compound nitrogen plus with oxygen. Now nitrogen can make many oxides with oxygen. Let's say it makes NO. When nitrogen combines with oxygen, its oxidation number is +2 because oxygen is more electronegative and wants to be -2. Let's look at up here for nitrogen trichloride. When nitrogen makes a compound with chlorine, its oxidation number is what? If this guy's negative, this guy has to be positive. Now, is there a time when nitrogen will become negative? Well, if you combine nitrogen with magnesium, you will make magnesium nitride. Now notice the shift. The formula for magnesium nitride is Mg3N2. Now what's the oxidation number on nitrogen? It is -3 versus magnesium, which is +2. Those are oxidation numbers. Nitrogen was more electronegative than magnesium, hence the oxidation numbers as indicated. So you can see that this table hopefully is making a little bit more sense to you as far as why these oxidation numbers are what they are. But you'll notice fluorine, always -1. So it doesn't matter what he combines with. He is more electronegative and will always take the oxidation number of -1. So let's look at fun sheet number 5. Fun sheet number 5 is asking about covalent bond and electronegativity. So given 4 atoms that have certain electronegativities as indicated, you're asked, how would you arrange these molecules in order of increasing ionic bond character? So for example, if I combine D and E, if I make a compound between D and E, its electronegativity difference is 0.5. What does that mean as far as what kind of bond is that? Is it ionic or covalent? Once you figure all these things out, your goal is to label each as ionic, non-polar covalent, or polar covalent. Explain why you think that is. And also to draw a bond moment on each bond that is formed. So for example, for DE, my bond moment would point towards the more electronegative atom, which happens to be D in this case. So my bond moment would look like that, where you have a partial positive on the E and a partial negative on the D. Now I ask you to keep in mind the size of your arrows, because let's look at a different example. If you combine E with G, for example, the difference in electronegativity is 2.0. Now this E combined with G has created a larger bond moment, and that bond moment is pointing towards the E, and it's larger because its difference was 2.0 that created that bond moment. Now, is that ionic or covalent? Let's talk about that in our next slides. So when we have a difference in electronegativity between two atoms of 0, that bond type must be purely covalent. There is no partial positive or negative. If it is greater than or equal to 2, it is ionic. Now this is a big gray area, and you will find different textbooks telling you different things, but just in general, as long as you can explain the differences between these things and how they were determined, that's okay. In between 0 and -2 is a polar covalent bond. So the increasing difference in electronegativity, the more ionic the bond. So if you have a difference of 0, purely covalent, in between there somewhere, polar covalent, and if 2 or greater, ionic. This figure out of your textbook is showing you how that electronegativity difference causes an increase in ionic character. So these compounds at the top are ionic. They're all ionic, but you see how there's a varying degree of ionicness, if you will, just like there's a varying degree of covalentness. Something like Cl2, where they're both the same atom, that is purely covalent, where something at the top, up here like lithium fluoride, that would be purely ionic, but again, a lot of gray area. So let's do an example. If we want to classify the following bonds as ionic, polar covalent, or covalent, let's try it. Cesium has an electronegativity of 0.7, chlorine 3.0. The difference is 2.3. Given this large difference in electronegativities, we would predict an ionic compound would form between cesium chloride. Now let's talk about the bond in H2S. Hydrogen's electronegativity is 2.1. Sulfur is 2.5. The difference is 0.4. We would probably predict polar covalent bond. Nitrogen electronegativity is 3.0, and nitrogen is 3.0. Now what this example does not show is the Lewis structures. Now a Lewis structure of cesium chloride this is an ionic compound, so you would see what you would call kind of not a Lewis structure. It is, we put a square brackets here, we put a square brackets here, and we say this is negative and this guy's positive, but we put no lines because a line would indicate covalent. In hydrogen sulfide, we might draw something like this. Here's an S, and we go down to H, and then we put our lone pairs on the sulfur. And I'm drawing this in what's called a bent fashion because it takes this certain shape, and we'll learn about that in chapter 10. But now this is a polar covalent. These are polar covalent bonds that I'm pointing to right here. That means there's more negative, there's a partial negative on the sulfur and a partial positive on each of these hydrogens. Now, as far as this next compound, it's asking you about the N-N bond in H2N-NH2. Now, if I were to draw that, as far as the Lewis structure is concerned, we're going to learn more about how to do these ourselves in the rest of chapter 9. It would look something like this. But what I'm focusing on is the bond, not between the nitrogens and the hydrogens, but between the nitrogen and the nitrogen. And since these are the same elements with this element with the same electronegativity, we would predict that to be purely covalent. So look at Fungi question number 5. It's asking you some things about whether they're going to be polar covalent or ionic or purely covalent.